37,000 feet over the Atlantic, a Boeing 777 is carrying roughly 300 passengers. Beneath them, under the cabin floor, sits some luggage, some cargo containers, and not much else. The real weight, the enormous, sloshing mass that makes this 14-hour flight possible, is not below the passengers. It is beside them. Stretching outward from the fuselage, hidden inside the wings they casually glance at through oval windows, are approximately 127,000 kilograms of kerosene. That is more than the weight of every passenger, every crew member, and every suitcase combined. Most people look at a wing and see an aerodynamic surface, a thing that generates lift. But what's actually happening is far more complex. The wing is not merely a lifting device. It is a structural beam, a fuel vessel, and a carefully balanced counterweight all at once, all by design. So here is the question that almost nobody thinks to ask: why store fuel inside the wing at all? An airplane already needs a fuselage. It already has a belly. There is, on the surface, no obvious reason to pump tens of thousands of liters of explosive liquid into the very structures responsible for keeping the aircraft airborne. And yet, virtually every large commercial and military aircraft built in the last 7 decades does exactly this. The reason turns out to be one of the most elegant structural solutions in all of engineering. The story begins with a problem that has nothing to do with fuel. It begins with bending. When a large aircraft sits on the ground, its wings droop slightly under their own weight. The moment it lifts off, the situation reverses. Lift acts upward along the entire span of each wing, while the mass of the fuselage passengers, cargo, structure pulls downward at the center. The wing root, where the wing meets the body, becomes the fulcrum of an enormous bending moment. On a Boeing 747, that bending load at the root can exceed several million Newton meters during a steep CL. Now consider what happens when fuel is placed inside the wing. Fuel has mass, and that mass acts downward under gravity, working against the upward lift force distributed along the span. In effect, the fuel is not dead weight that the wing must carry, it is a counterbalance that reduces the net bending load the wing experiences. Think of it like carrying 2 heavy grocery bags, one in each hand, versus strapping all that weight to a belt around your waist. The bags in outstretched hands create enormous torque on the shoulders. But if that same weight were somehow distributed along the length of each arm, the shoulders would barely notice it. That is precisely what wing fuel does. Not added burden, but structural relief. But that raises another question. How much difference does this actually make? The numbers are striking. Engineers at Boeing and Airbus have noted that for a wide-body aircraft, wing fuel can reduce root bending moments by roughly 25 to 30% compared to an equivalent aircraft carrying the same fuel mass in a central fuselage tank. That reduction translates directly into thinner wing skins, lighter spar caps, and fewer reinforcing ribs. In other words, storing fuel in the wing allows the wing to be built lighter. Not heavier. Lighter. The common intuition. That filling a wing with fuel must demand a heavier, more robust structure is precisely backwards. And this is where another limit begins to dominate, because bending relief is only part of the story. The wing also has to deal with a phenomenon called aeroelastic flutter. At high speeds, aerodynamic forces can interact with the natural flexibility of the wing to produce oscillations that grow in amplitude until the structure fails. Flutter is not hypothetical. It has destroyed aircraft. The key to suppressing flutter is to keep the center of mass of the wing close to or ahead of its aerodynamic center, the point where lift effectively acts. Fuel stored inside the wing, particularly in tanks positioned near the leading edge or across the forward spar, shifts the mass distribution in exactly the direction that raises the flutter speed threshold. The wing becomes not just lighter in bending, but more resistant to the very oscillation that could tear it apart. Not a fortunate coincidence, but a deliberately exploited physical relationship. But that still leaves a practical objection. The wing is not a hollow box sitting idle, waiting to be filled. It is a complex lattice of spars, ribs, stringers, and skin panels. Where does the fuel actually go? Here, the answer reveals another layer of efficiency. In most modern transport aircraft, the wing box, the primary structural core bounded by the front spar, rear spar, upper skin, and lower skin. doubles as the fuel tank itself. The structure is the container. Engineers do not insert separate fuel bladders or rigid tanks into the wing the way fuel cells might be installed in a race car. Instead, they seal the joints between structural panels using polysulfide sealant compounds, turning the entire wing box into what is called a wet wing or integral fuel tank. Every rivet hole, every panel joint, every inspection access point must be sealed against leakage. The result is that the same aluminum or composite panels carrying flight loads also hold fuel. Not two systems occupying the same space, but one system performing two functions simultaneously. This dual-purpose approach saves an enormous amount of weight. A separate fuselage tank system capable of holding 200,000 liters of fuel, the capacity of a long-range widebody, would require its own walls, its own structural support, and its own mounting hardware. Estimates from aerospace structural analyses suggest that a dedicated fuselage tank system could add several thousand kilograms of empty weight to an airframe compared to an integral wing tank design. In commercial aviation, where every kilogram of empty weight translates to roughly 3 to 5 kilograms of additional fuel burned over the aircraft's operational lifetime, those savings compound enormously across a fleet and across decades. But there is yet another dimension most people never consider. Fuel placement is not fixed during flight. As engines burn kerosene, fuel is consumed from specific tanks in a deliberate sequence managed by the fuel management computer. This sequencing is not random. It is choreographed to maintain the aircraft's center of gravity within a narrow acceptable range and, on some aircraft, to actively manage wing loading. The Airbus A380, for instance, carries a trim tank in its horizontal stabilizer, and fuel is transferred aft during cruise to shift the center of gravity rearward, reducing the aerodynamic downforce the tail must produce, which in turn reduces overall drag by a measurable percentage. Not a passive reservoir, but an active ballast system, constantly rebalancing the aircraft in flight. So if wing fuel storage is this effective, this elegant, why not push the idea further? Why not extend the fuel all the way to the wingtip, or make the wing even larger to carry more? The answer lies in a cascade of constraints that close in from multiple directions. First, the outboard sections of the wing experience the greatest deflection during flight. Wingtips on a Boeing 787 can flex upward by roughly 3 meters in turbulence. Fuel tanks in highly flexible zones face severe fatigue stress on their seals, and sloshing dynamics in an outboard tank could introduce unwanted mass oscillations that actually worsen flutter rather than suppress it. Second, fuel in the extreme outboard wing increases roll inertia, the resistance of the aircraft to rolling motion, which degrades handling qualities and demands larger, heavier ailerons. Third, lightning strike protection, maintenance access, and leak detection all become exponentially more complex as tanks extend outboard into thinner, more cramped wing sections. And then there is the ground reality. A wider fuel-laden wingspan means wider taxiways, wider gates, and higher airport compatibility costs. The 80-meter gate span limit at most international airports is already a hard boundary that constrains the wingspan of aircraft like the A380. Every meter of additional span is a meter of infrastructure cost passed along to airlines and airports worldwide. The current fuel tank arrangement in a modern wing is not a partial solution waiting to be optimized. It is a precise equilibrium between aerodynamic efficiency, structural relief, flutter suppression, maintenance practicality, and airport-level infrastructure. To step back from the engineering and consider what this really represents is to see something quietly remarkable. The wing of a commercial aircraft is one of the most multifunctional structures ever mass-produced. It lifts the airplane. It carries the fuel. It counterbalances its own bending loads. It suppresses its own flutter tendencies. It acts as a dynamically managed ballast system that adjusts the aircraft's trim in real time. Not 5 separate systems bolted together, but a single integrated structure doing 5 jobs at once. I find that this is what separates truly mature engineering from clever invention, not the addition of more systems, but the merging of functions until the boundaries between them disappear entirely. The wing does not merely hold fuel because there is room. It holds fuel because the fuel makes the wing better at being a wing. Not by accident, but by a chain of physical insights accumulated over nearly a century of flight, refined through failure, validated through millions of hours in the sky. Have you ever wondered what happens to an aircraft's structural behavior in the final minutes of a long flight, when the wing tanks are nearly empty and all that carefully balanced counterweight is gone?